Hello everyone. Test. Okay. Should all be working. Welcome back to the stream. If you have been here the past 2 days, then you notice that I'm sitting in a different environment here. I've rearranged my room because I was unsatisfied with the place how I was working. Like the general setup, and so yesterday after the stream I spent a couple of hours completely rearranging my setup, and let's see how it works out. Maybe the angle is a bit weird because this is where I would usually work on these two spots here, and here I have the setup now for building the 8-bit computer that we are building, but I have way more space now, as you can tell, and you don't quite see it here, but let me show you the top-down camera. So this is now, I think, looking much better. And we can then also move the camera forward, where we then have the oscilloscope and also the power supply and stuff like this. So if we look at some stuff, we have the oscilloscope right here in view. That should be great, I think. Yeah, I'm really excited about this. I think this is cool. Okay. Yeah, I'm still waiting on a few things. As you can see, I have here the the overhead camera here, like this. What's the name? The tripod on the table and stuff. So I want to get a proper desk clamp to go like overhead or something like this. The cable here is not so nice. But yeah, still working on it. Also not sure about the microphone position right now. But I think it's better than it was before, because it's kind of like now over here, just out of reach of the camera, and depending on if I'm here or here, it should be all good. Yeah, that's about it. That's the new setup. Let me know what you think. Do you have a favorite meme from last month? I'm not sure how many people in here are watching a lot of Twitch, but I have thoroughly been enjoying the Miskiv and Maya memes. So what are you going to use this 8-bit machine for? Well, for education, for learning. I want to build this. If you haven't seen it, let me show you here again what this project is about. Ben Eder has this series on building an 8-bit computer from scratch, where you are, building the whole machine. Here, let me just show you really quick again, screen of that. There we go. That's the 8-bit computer. So I want to build that as well, follow along his video series, and learn a bit more in more detail about how a computer actually works. And so this is an 8-bit computer, just because more bits would be crazy to implement by hand. The end goal is, if we build this, maybe we want to build some extensions to it as well, because it only supports 16 bytes of RAM, which is not quite a lot for implementing programs and such. But then eventually I want to maybe, hang it at the wall or something like this. I think it would be like a cool art piece. I think it looks cool in the background. And yeah, just for the learning content, that's the main goal. Hi Narek, have you been doing many CTFs recently? I haven't been doing CTFs a lot for the past 2 years or so. It feels really bad. I really don't get so much time anymore. I don't know. So it's like sporadically a few CTFs here and there. From a scale from 0 to 10, how would you describe your knowledge and what you're going to do right now? Well, I think I have some basic understanding of electronics, very amateurish. I have played around with Arduinos and have made a very simple, PCB with just a few LEDs and a shift register. That's about it. So I don't think I could, for example, build this 8-bit computer just by myself without instructions. I think, so my level I think is I will be able to understand how it works once I follow this guide, but I wouldn't be able to do it myself. So that's kind of the level where I expect myself. Your workspace really looks much tidier. Did it not look tidy before, or what do you mean? Are we going to hear thunderstorms in your area during the stream? I have no clue. I didn't check the forecast. Could be. It's pretty warm outside. Let's see. I didn't hear about any. It's actually, you're jealous of the big workplace, so it's actually not big. I mean, it's a small room. Like that, basically, there's a little bit of space like in front of me, but not as much as there's behind me. So the room is relatively small, but I'm super happy with the rearranging it like this. It feels way more cozier to have like the curtains behind me. I have the small space now here around me, like here I'll write the curtains, you know. So it feels very cozy and way more relaxed than it was before. And the way how I positioned the tables now, I feel like I get more out of the desk space as well. And obviously how the camera is set up with this cone in front of me, so it looks like I have a lot of space here. But yeah. In the south, their storm already ended. Interesting. So looking at the forecast, no, I don't see any. There might be rain in the night, but no thunderstorm. Yeah, don't intend to stream for that long. Awesome. Are you later going to program a compiler with a higher level language for the computer? I'm not sure if that will be possible with this version of this computer. I haven't looked at it in detail because I'm just following the series now. I haven't watched the videos beforehand, but I read a few pieces here and there. And my understanding is that the instruction set is extremely limited on here, and I mean, you have to implement all the instruction in hardware yourself. So basically, as far as I know, Ben Eater has just implemented a couple of kind of important instructions, but then again, this machine only has 16 bytes in the default configuration. 16 bytes, which allows you, you know, a few bytes for instructions and maybe a few bytes for memory as RAM, right? So he has this Fibonacci program that uses like, I don't know, like 14 bytes or so, or 13 bytes, and then it uses like 3 bytes as memory to store the current value of the Fibonacci, for the Fibonacci algorithm, right? The temporary variables. So there's not much space. So, but you know, let's make some progress with this, because I do wanna, you know, iterate over it myself or improve on it myself. Like increasing the memory, that would be cool, and also maybe implementing more instructions. But that is definitely something that we figure out at a later point. As of right now, I don't know yet why he was only able to do like 16 bytes and what it would take to make it addressable, being able to address more memory. But we will learn about this, right? Like this is, I guess, we will learn about more internals about computers, about how addressing works and why this only has 16 bytes and stuff like this. I'm really excited about this. You came here to watch the dog. I'm sure the dog will join us soon, because she has to go to the store later and will drop the dog in here because he has separation anxiety and he will freak out. So I'm sure the dog will join us soon. Yeah, we see more. Yeah, awesome. You do realize that you will have to go through the tedious process of programming the EEPROM for processing commands. Yes, I have seen that, and I think didn't he also add a module with like an Arduino to let the Arduino program the EEPROM? Yeah, for sure. I know that would be fun though. Okay, awesome. So I think get started. Let me show you what we did. The state of yesterday. Camera. There we go. So we built this yesterday. Let me show you. So this is the clock module. This is the first part of the series where we are building the clock of the computer. And we are on the second video of his series right now. So let me see. So what we have built is the first circuit up here. So this chip is called 555. Yeah, it's a timer chip. You are able to use it, it's a very versatile chip, as we have learned in the stream. Anyway, you can see basically that's a clock. That will be the clock signal of the computer. And we have here this potentiometer that allows us to change the resistance, which affects on how fast the clock will run of this computer. So this is now running so fast that it looks like the LED is consistently on. And yeah, we can slow this down, basically so slow that we can really look at, see each clock cycle of the CPU slowly executing the programs on the machine. So this will be so cool. So this is the general clock signal, but Ben Eder wanted to also, for debugging purposes, be able to advance the clock only when we want it to go forward. So we added here this button that can also automatically, triggers it. And we are also using here the same chip for reasons of glitches, because these buttons are, metal contacts, and when they join together, they might bounce a little bit, and then you might get accidentally more clock cycles than you wanted from one click. So with that, you can debounce the press so that it's really just triggering the LED once. And I believe, or I suspect that in the third video now we somehow will combine these, or add a switch that we can decide if we want to have the automatic clock or if we want to trigger the clock by hand for debugging. Yeah, so that's what we built the past two streams. Are you going to replicate it? Yeah. I mean, I assume you're talking about the 8-bit computer. That's the goal. The goal is to build the whole computer and also kind of replicate. That's what the oscilloscope is for, to also look at how this stuff works. Can you build a CPU? I don't think so, but I'm sure I will be able to follow a guide of somebody who can and build it based on the instructions. Okay, so then I think it's time to head into the third video. Sorry, we need to switch here to desktop, and I should maybe move my face. How many breadboards do you need for this project? So on Ben Eder's website, you can find a parts list. I think there's 14 breadboards or something like this, and I have them all sitting there. I've ordered all the parts. Yeah, on this website, you can find here a complete parts list. He has used 14 breadboards. On how much estimated time on how much it will take to make an actual computer. I mean, that is a computer that is executing instructions and stuff like this, or what do you mean? Can you recommend any CTF challenges for beginners? I'm not so sure. I mean, I think the Exploit Education series, what used to be Exploit Exercises, is a great series to start, and you have my videos that help you when you get stuck. So you can, watch some videos and try it yourself and stuff like this. So I think that is hopefully a good experience. Otherwise, I think also Pico CTF is probably a good place to start. I think these are good places. After you finish to build your stuff, connect the motherboard by USB to see real performance if it is possible. I'm not sure what you mean by that. Okay, so let's watch this video. Sound.
So in the last two videos, we used these 555 timers to build an astable circuit with the pulsing output, and a monostable circuit that's normally off, but when we push the button, it turns on and it's debounced so that we get a single clean output when we push the button. So this we can use for our clock, and then we can also use for a manual pulse. Now what we need to do is figure out a way to switch between the two. And so you might think, well, we should use a switch. And I've got a pretty good switch here. This is a little push button switch, and it's either out or in, and it's got these three leads. And so there's a center common pin, and then it's connected to either this pin or this pin, depending on whether it's in or out. And there's two, so that's double throw, it's called, and then it's double pole as well. There's sort of two sets that are independent that are just connected to the same button. So double pole, double throw, and that's a fairly common type of switch. This is another switch here that's the same thing, and you've got the two sets of three connections there. Of course, this doesn't plug into my breadboard. And annoyingly, neither does this. This is actually just a little bit too, this pin spacing is a little bit too close together to fit into the breadboard. And so what I've done is gone ahead and soldered these little header pins to the switch. And so that fits in very nicely into the breadboard. And so one thing we could do is we could just connect the output of this here. Well, that's not the output. Let's connect the output of that to one side of the switch. And we could connect the output of our manual trigger over here to the other side of the switch. And then we could look at the middle of the switch, connect that to an LED. And then, of course, our current limiting resistor here. And we see that it's pulsing. And then we could flip the switch here, and now it's connected to our manual clock pulse. And we could flip it back, and it's connected to the sort of automatic clock pulse there. So this is great. We could use this. This will work. One problem with it is, again, we have the switch in here that's not debounced. And so we could have some situation where, maybe we have a really slow clock pulse, and we're going step by step by step, and we're watching our computer execute. Maybe we're troubleshooting some problem, and we're watching it go step by step, and then we see the problem that we're trying to catch develop, and we push the button to try to get it back into manual clock pulse to stop the computer, and so we can figure out what's going on. Well, if when we push that, we have that debouncing problem, and we get a couple extra clock pulses in there when we were going so slow to catch that one point that we're trying to catch. That could be really frustrating. So we really should find a way to debounce this switch. And you could build exactly this circuit, and that would work fine. I'm going to show you a different way to use the 555 just for fun, just to see yet another use for the 555. And so for this next circuit, what we're going to do is we're basically going to take advantage of the fact that the 555 timer has an SR latch built into it. And we're really only going to use the SR latch. We're just going to kind of try to ignore the rest of this stuff as much as we can. And what we're going to do is we're going to basically hook this switch up to, imagine we could somehow get rid of all this stuff and just hook the switch up to the S and the R. So in one state it's setting, and in the other state it's resetting, and then we have our output. The SR latch will actually act as a debouncer, and one of the reasons it'll do that is kind of a property of these switches, which is if we look at the switch, if I just hook up a couple LEDs so we can kind of examine how the switch normally works, what you'll see is that it switches between the two states when we push the switch, which is what you'd expect. But if we push it very gently, you see it actually, you can kind of get it in between, and it turns off. And that's actually a pretty useful property. So it's called break before make. And you can buy switches that are make before break if that's what you want, but I think most switches are typically break before make. And so what that means is that it can be, if this is, say, our reset or our set condition, let's say we're putting a set into this SR latch. Forget the fact that it's part of a 555. Just imagine we're looking at an SR latch. If we're setting it and then we start to push this switch, as we let go, or not as we let go, as we push the switch gently, we're kind of in this middle region our latch is still going to be set, right? And then as we continue to push the switch down, we get into the reset. Then that reset comes on. Well, if there's any bouncing in the switch, it doesn't matter, because as soon as that first reset happens, the latch is reset, and our output is going to be off. And then the same thing, as we push this and then as we gently let go, the reset goes off. We're still reset, right, because we haven't set it yet. And then even if there's some bouncing as we go into the set state, doesn't matter, because as soon as it first sees that set state, boom, the output comes on. So we can use an SR latch as a debouncer with a switch like this. So the question is, if we're using a 5.5, well, we could use just an SR latch on its own, which I've got a video that shows how to build one. But we can use the 5.5 timer. We can use its SR latch by essentially using the trigger, right? So remember, we've got 5 volts up here, right? And then we've got this voltage divider network. So this gives us 3.33 volts here and 1.6667 volts here, and then of course 0 volts down here. And so if this trigger goes below 1.6 volts, then that sets the latch. And then if the threshold goes above 3.3 volts, that resets it. But we're actually going to ignore the threshold. We're going to just tie this to ground. And so this will never do anything. Instead, we're going to use pin 4, which we haven't used yet on the 555, and that's this reset pin. And it's not wired exactly like this in here, but you can kind of imagine it. But this just gives you kind of a shortcut to the reset. And so if we pull pin 4 low, because it's inverted, that resets it. And if we pull the trigger low, below 1.6 volts, that will turn this comparator on and set it. And so that gives us a way to kind of get into this SR latch. And so what we can do is we can hook our switch up, sort of draw the switch down here. And so we can hook our switch to ground, the middle connection of our switch to ground, and we can hook one side up over to our reset and hook the other side over to our trigger. And then if we flip our switch over to this side, that'll ground the trigger, which takes this now below 1.6 volts. We should probably have a little pull-up resistor here of some sort, maybe a 1K resistor will do, so that normally, this is going to be 5 volts, so it'll be well above our 1.6 volts, and so this will be off, and so we won't be setting it. But then when we flip our switch here, and this goes to ground, that'll pull this down to 0 volts, and 0 volts, of course, is below 1.6 volts, and so that'll set the flip-flop, and the output will turn on. And then when we flip our switch over to the other side, we do that break before make, which this diagram actually shows pretty well. When we break, no big deal. We're not setting it anymore, but it's a latch, so the output stays set. But then when we first make contact over here, even if it bounces, it doesn't matter. The first time we make contact over here, we reset the latch, and then the output turns off. And so we have this nice debouncing that we can use. So let's hook that up. Okay, here it is. So we got our switch here, and the center pin is connected to ground, which is what we wanted here. And the other 2 pins, one is connected over here, you can see, to pin 2, and the other one's connected to pin 4. And so just like we've got here, so one's connected over here to pin 2, that's our trigger, and the other one's connected over here to pin 4. And on both of those I have pull-up resistors. So you can see on pin 2 and pin 4, I've got a resistor going to 5 volts. I didn't draw that over here, but we want to make sure that these are normally getting 5 volts unless our switch is set. Pin 3, of course, is our output, so I just have that going to this LED for now with a current limiting 220 ohm resistor over there. And then pin 6 is our threshold, so we have that just at ground. So this comparator is never going to be on. So we don't have this resetting this way. The only way we're resetting the latch is through our reset pin. So threshold is to ground, and then pin 7 is our discharge pin. No need to connect that. We're not discharging anything. There's no capacitor in here. So we just leave that disconnected. And then pin 5, as usual, we have our little 0.01 microfarad capacitor in there for noise, as recommended. So now what we've got is you push the button, the light comes on. Push the button again, the light turns off. So not very exciting, but it is fully debounced, and we're using the SR latch part of the 555 timer. And so with that, we've actually got the sort of 3 different modes that you can use the 555 timer in. We've got the astable mode, where it's not stable in either state. We've got the monostable mode, where it's got one stable state, which is off, and then when we push this, it goes to its other state, but then reverts back to the state that it's stable in. And then this is the bistable mode, where it has 2 stable states, and so it's either in this state or that state. And so now all we need is a bit of logic to combine all 3 of these into our final clock output, and we'll do that in the next video. In the last couple of videos, we built our
All right. Let me quickly wait. Let me quickly catch up with chat. Have you seen the videos beforehand, or is it gonna be we watch the video together, you try to replicate it? Yep, that's basically what it is. I haven't really watched the videos, I just know about the project. I've just clicked in a couple of videos just to check it out. But yeah, if I want to build this right now, and to do that I have to watch the videos, and I do that on stream basically. Is it gonna be a video per stream? This seems to be how it is turning out to be as of the first 2 videos at least. Have you played the Faust CTF? No, I have not. If you want to learn electronics, great way to start videos from Great Scott. I have not really watched that channel, but it looks like a very amazing channel. Yeah. Are you going to make a video on this? Unlikely, because there are the Ben Eater videos, which are perfect already, so I don't see any reason why I should just make the same videos too. However, of course, I'm streaming this right now, which is producing a video in the end, a VOD that you can watch. So the VODs are archived on Twitch, but they are also archived on YouTube. Not on the main Live Overflow channel, because I don't want to annoy people with these long unedited streams kind of stuff. So you can find the raw streams on a second channel of mine, and I have also started to create like highlight cut videos, just a condensed version of the stream as well, just a very rough cut, just to cut down the time a bit. Not sure if I can keep that up, but it's the plan for right now. The channel is called Random Overflow, and you can find the link in my YouTube channels, like related channel descriptions or something like this. Electro Boom. Yeah, Electro Boom is awesome. Love those videos. Are you attending DEF CON this year? No. Unlikely. Thanks for the cheer, newbies. How much do the components of the computer cost? It's again, check out the parts list on Ben Eater's website. It's roughly $250. Plus minus depending on where you buy parts. I paid roughly 240 euros right now, I think. The most expensive parts are the breadboards. I think the breadboards alone were easily like 120 euros or so. Different questions. Have you been at the Cybersecurity Challenge Germany in the past? Yeah, I played it 2 years. And yes, I'm a freelancer. Okay, all right. So let's quickly build that. Actually, so one thing I've been, I need to gather the parts. So I don't really still, has anybody understood like the difference between the previous debouncing circuit and now the one we built right now? They still seem to fulfill the exact same purpose. I don't understand why the monostable is so different from the bistable, because the monostable is also, if the switch is triggered, it's on, and if you release it, it's off. Isn't that the same thing as a switch being, switched on and then it's glowing to the other off? So I don't quite understand the difference, and maybe depending on how we have time, I wanna compare those two again and try to understand what the difference is. Oh, Procker, thanks for the subs again. You gifted some subs already yesterday. That's absolutely not necessary, but thank you so much. What's the random? Yeah, it's probably, let's see. It's a URL. If you go on liveoverflow, and then you go on featured channels, it's right here, random overflow. And there are there were only 2 streams so far. You can find the highlight cut of the 2 streams and the full stream. I don't know how many components I will kill. Maybe because you need to debounce both states here, and previously only had to debounce the on state. That makes sense. That makes sense. Yeah, you're right. The off state debouncing doesn't matter here because I guess yeah, I'm sure you are right. It hasn't clicked yet in my head, but that also is the only thing that makes sense to me. You don't have to debounce a 0. Yeah, it's like weird. Well, let's build this and then let's see. So here are the timers. I need to pull up the thing he built here. Part 3. 1 second. Okay, let me see. I could. Yeah, that should be fine. We can unplug this for now. Turn it off. Get this over here. So we need green, black, and red wire. The others fall down. Oh no, where did they go? Oh wait, they are here. Black, red, and this greenish color. All right. Yeah, I chose random overflow in the end. I don't know. Well, it's still like, I don't know. There's still time to rename it. Maybe I come up with something better. Yeah, there's a difference between 0 and floating. One is ground and one is just undefined. If I remember correctly, he said you could use the old debouncer too. Oh, he did say that in the video? Actually, wait, maybe he did say that. Wait, let me see.
Essentially using the trigger, right? So remember, into this SR light. Forget the fact that it's part of 505. Just a couple LEDs so we can kind of examine how the switch. And so what that means is that then we start to push this switch, then that reset comes on. Well, if there's any bounce
I think it was a bit earlier.
Up to, you know, imagine we could somehow get rid of all this stuff built into it.
I think it was when he connected these wires, right?
That the 555 timer has an SR. If we look at the switch, if I just hook up a couple LEDs, so we in this middle, some bouncing as we go into the set state, doesn't matter, because as soon as it's first, this will never.
Here's it already describing. Where does he mention the motivation again?
Is kind of a property of these switches. The SR latch will actually act as a debouncer in the R. So in one, exactly this circuit, and that would work fine. I'm going to show you a different, really frustrating. So we really should find a way to debounce this switch. And you could build exactly this circuit, and that would work fine. I'm going to show you a different way
there it is.
To use the triple.
You are right. You were right. Awesome. Thanks for pointing that out. Who said that again? Lazandre. Thanks so much for pointing that out. That was very helpful. Okay, so it wouldn't matter if we built the same circuit. He was just building another version of it. Okay, so what else do we need? We need... Okay, so we got the wires. We need the 0.01 micro Farad capacitors again. These here, we need an LED. And resistors he's using here. I think these were all 1K resistors. Now 1 second. Okay, the resistors here, and the switch. So let's see, I bought these switches here. Let's see if they work out as intended. Thanks for the sub, Alice Cool, Alice Bestons. Look, we got emotes. We got one emote. It's the glitch. Okay, we need the pliers. There we go. Cool. I really need, I think, a monitor here just for the chat, so I can kind of look in the camera and read chat and not always like turn away like that. So dang. I thought about trying to also submit just the red circle for, I mean, so far we only got one emote, but again, can just shout out again, Soding is very active streaming, streaming C++. It's also very interesting and entertaining. I can recommend to follow. Okay. Great. Okay, so let's build this. So he was putting it 2, 4 like that. A white rabbit. That's a good idea too. I hadn't thought about that. Yeah, that makes sense. We totally need a white rabbit. Who of you are not from or who of you don't know Club Mate, by the way? 1 in chat if you don't know it. 2 if you know it. I tried to build the circuit on a PCB today. After the oscillator, I noticed that I have basically all components, but not one switch. Way too many ones. You really need to travel to Germany with some time. It has a. You can look it up on Wikipedia. Oh, god damn it. Club Mate. Clubmate. You prefer the Mio Mio Ginger? You hipster. Okay, so then we want to add, we need some, it's German Red Bull. Yeah, it's a high caffeinated soda drink. It's based on mate tea. But it's like why I'm mentioning it is not because it's an interesting drink, but because it's like part of German hacking culture, and so it's very popular in the German hacking communities, and it really helps you to like stay up all night and work on something. And I think it's even mentioned, at least on, I think on at least the German Wikipedia, it's mentioned that it has its like big origin kind of in the German hacking culture. They sell it at a vending machine directly on our campus. That's nice. Oh no, ooh. There we go. First one. Okay, wait, I need to, I want chat in front of me. Let me pull up chat on my phone. You got through 35C3 without drinking mate once. That is pretty impressive. Oh, you got my sticker? That's cool. Okay, so now I have chat on the phone, hopefully. Okay, so now I can put... Oh, crap. Stop. Don't... Why are you making noises? Can I pop out the chat somewhere while you're here on mobile? Okay, let's see. All right, okay, so let's continue here. What kind of finale were you talking about? Sorry, I think I missed what you were talking about. Oh, the cybersecurity challenge. Yeah, I played in like some of the earlier ones when it was happening, so it was like, I guess easier to get into. Yeah, not the best challenges in that event. Definitely not. So these were, I think, 1K. I should buy a wire stripper. Yes, indeed. We talked about it yesterday on stream. Some people recommended some wire strippers for me, and I ordered one. Hopefully arrives. I don't know. Maybe even tomorrow. Otherwise, sometime this week. I think I have to strip a lot of wires, and yeah, I don't know why I didn't order one earlier. So this goes to pin 2 and VCC. Oh wait. I need to put this one higher up. Yeah, the challenges are most of the time guessing. Yeah, it's not a good CTF. However, like the good thing about like why I still liked the CSCG was because I met a lot of amazing people that I'm still that have become really good friends of mine, and we have basically our CTF team formed through that, and so that's why I really, you know, the CTF might be shit, the challenges might be crap, but in the end there's a community around it with people, and I really enjoyed that. Just tuned in. What step are you on? We are on the third video. We are here on the still on the clock module, and we are following the Ben Eater's series on building an 8-bit computer. I think, wait, did I add I think I added a command. No. Topic? No. I thought I added a command. I'm doing at this moment the Z transform for school. I'm not sure what the Z transform is. I'm participating since, but this time got in the finale for the first time. I believe it's a great way to find friends who are interested in the same topic. Yeah, for sure. So it's a clock. Yeah, it's a clock module. We will plug it in a second, and then you see the LED blinking as the clock. Oh, my screen. Sorry. There we go. You're participating since around 2015? Maybe then we have interacted before. I didn't play as liveoverflow during that time. S transform to Z sample data simulators pit tuning. You see? Okay, I have no damn clue what you're talking about. But sounds like a lot of math, like algebra or something. So this goes into the LED goes into the third pin and down there. So like here, and this goes up to there. To the third pin. Okay. Don't think so. Was around 25. So, well, I don't know. Maybe you were still hanging out in like the IRC channel or something like that. There we go. And then we need the, what was it, like for the limiting resistor for the LED. I think we used like 220 maybe last time. I think so. Is that a JK flip-flop or not? You mean this here? Like the chip here? Or what do you mean? Okay, this could have been bad. I just realized I plugged in the resistors in the wrong pins. These one go to VCC and only this one goes to ground. The KSU drawn. I didn't draw any. What do you mean? So we need the screen wire here, and we have going 4 up. Like here. There is no KS. The wait, sorry, wait. What is KS? Isn't KS like a truth? KS diagram. I might confusing it. A block. Yeah, okay, block diagram. I didn't know. Wait, KS. Oh, I'm confusing it, I think, with KV diagram. Oh, sorry, I confused it with the KV diagram. What you were saying. I didn't know that. Yeah, okay. So the block diagram. So this is from the video from Ben Eder. It's the 8-bit computer clock part 3. It's the inside drawing of the 555 IC chip, and it's an SR latch. Yeah, excuse my ignorance with the with the terms and stuff like this. I'm very much an amateur. I'm actually not running this in this Ubuntu here in a VM. It's here my ThinkPad. What would you recommend to study in Germany, university or FH, applied informatics or general informatics or IT security at some FHs? Can you recommend a special university? First of all, I cannot make any... crap. I cannot make any decisions for you. You have to figure out yourself what you want to do. My opinion has zero... has zero importance. However, my advice would be basically, or what I think, god damn it. My advice generally for studying is that you should focus on what seems fun to you. Because university can be very stressful and very difficult at times. And so if you are not in a subject that is motivating you to grind through the difficult and the hard parts, then... What is going on? This one broke too. Yeah, so I was saying if you don't have fun in the overall subject, because then the struggle of certain subjects will be too much. And I think like the best parts of university is not necessarily like I don't know, it's like your environment, like the friends you're gonna make, the study groups you will have, studying together, learning together with people. I think those are the things that help you the most in the end. And so it's very difficult to say which university that will provide that, because basically it depends on if you find like a good social circle at university or not. One second. And so, also that being said, I have not heard a lot of good things about generally the topic of information IT security as a subject, like as a degree at least if you are very technically motivated. I don't think that degree gets you a lot. I've heard that it's like, I don't know, like I haven't heard good stuff about it. I felt what I've heard is that you learn a lot of like management stuff that might be very important for the industry, but I feel like, for example, I wouldn't like it because I'm way more interested in like the technical stuff, and I wouldn't want to deal with all the other stuff around it. I also feel like that IT security in general is like a topic that builds upon general IT knowledge. And so I feel like starting to study this without having any informatics background, I don't know, feels weird. Also, I have not studied at different universities, so I cannot compare them. I cannot tell you which one was great. I'm studying in Berlin. I didn't study there because that was like somebody told me it's a perfect university. I went there because friends went there and I was lazy and they could tell me how all the bureaucracy works. Yeah, so that's about it. Okay, that switch is like really janky. It's like really hard to push and it's like not sitting tight in there, you know. Maybe I need to check in a second if I have alternatives. Hot glue helps. That actually makes sense, yeah. I'm not sure if I want to sacrifice the boards already to hot glue, but maybe at some point just to make sure everything sits tight, especially if I want to hang it or something. That seems reasonable. How does German university system works? Is there any entrance exam? That depends on what you're going to study. Generally in IT there is no basically no requirements except that you have to have an eligible like high school degree. So that's in Germany, that would be an Abitur. And if you are coming from a different country, then basically your degree from that other country needs to be equivalent to the German Abitur, which kind of fucks over certain countries. For example, in the US, in high school, you can already have certain elective courses, as far as my understanding is, and the German Abitur, for example, requires that you know at least two foreign languages, or that you had two foreign languages in school, and two foreign languages, and so if you only had one or none in the US, then it wouldn't be equivalent and stuff like that. That changes if you go to a US university and then do an exchange year or something like this. Then it's again different. Then it's all fucked up. You can always use jumper cables. I really like your YouTube channel and how you manage to do all the fun things on your channel. Thanks. I'm glad you like it. You think surveys can help at some stuff? I'm not sure what you mean. What help with what? We had no entrance exam, but the first semesters were hard enough that enough people stopped studying. Yeah, so that's a typical pattern in German universities, that you have these extremely hard exams in the first semester to naturally select the people that can cry the most. Oh, thanks for the bits. Like a product you sell? Wait, what? You think surveys can help at some stuff? Like a product you sell? Sorry, I don't. And what's the context of? Sorry, maybe I missed even something earlier. What product are we talking about? Any idea where I can get into electronics? Probably would be better to start with something simple and useful rather than a whole computer. I mean, to be honest, like following the series, I think would be a great start. But otherwise, just like, I mean, I don't know what a good entry is, right? I'm not a professional. As a hobbyist, I can tell you that I thought that doing Arduino stuff was really helpful for me. Just getting like an Arduino starter kit and trying to build something with that. I also think like small stuff, maybe you can, like there are these kind of Arduino compatible things, I forgot their name, but they have Wi-Fi included. So that makes it very easy to kind of integrate with like your home network in a way that you can, for example, send commands from your computer over Wi-Fi to that chip, and then you can like control like some LEDs or something like this. I could imagine that that could be like a cool project to learn the basics. The second language is not necessary. With the Fachgebunden, so kind of specialized in the direction, you can also go to the... Yeah, okay, yeah. But then again, that gets complicated. I don't know. I don't like the German system, to be honest. I wish we would make it much easier for people to go to university. As, for example, also if you had Realschule before, that you can just like prove yourself in a certain way and like do an entrance exam, and then it would allow you in. I mean, make that entrance exam hard, I don't care, and make people be able to study. But if somebody spends like a year or so studying towards that entrance exam to learn it and then to get into studying later in their lives, I think that would be so important. I don't like our system, to be honest. Yeah, the ESP, that's the one I meant, yeah. For ESP, yeah. Yeah, I think that one, for example, is, I think, fun because it already adds a little bit of magic because it does like Wi-Fi, and Wi-Fi or Bluetooth is like already like super advanced kind of protocols. So it's not as low level as just like serial, for example. But I think it makes a first kind of application that feels useful a bit easier. And so I think you see successes faster and you can make yourself small little gadgets. Just wondering where your Sauerkleid shirt is. It's in my closet. I don't really like it either, but it got open up a little, like Meister would be kind of a wrong trend. You could study too with a Meister. Oh yeah, with a Meister, if you did like an Ausbildung, it's like if you go that path. Yeah, but that again is like super removed now, you got to do a Meister. And I don't really think that a Meister is then again equivalent like to... I don't think that, for example, I think a problem, for example, would be if you would want to go to university in chemistry or physics, where you have then really kind of advanced math. Meister degree wouldn't teach you the math stuff, and you would have to brush up on that anyway, but suddenly that allows you to go into it rather than somebody who's self-studying all the higher math stuff themselves to like be able to do it. I don't know. I don't like it. I think it's artificially limiting and is punishing people that decided later in life, or needed a bit of time to realize what they want to do with their life, and I think that's bad. Anyway, I think we implemented this. Let's plug it in and let's see if it burns. Yes, I think should be fine. So those circuits still work, so that's good. Oh, Adam, thanks for the host. You should also, everybody, check out Adam. Adam is developing for a super long time now already, like a browser game about automating bots and fighting against each other. And he's really great at streaming. I cannot comprehend how he can program and interact with chat so well as he does. It always amazes me. And he has been doing it for such a long time. He's super helpful and nice, and you should definitely check him out. Okay, so yeah, this at least seems to work. The switch allows us to change the LED. That's very exciting. You stream under the name liveoverflow. You should connect it to 230 volts. That will give those LEDs a little bit more oomph. True. Yeah, so welcome everybody from Adam's streams. It's very exciting here. We just finished this amazing circuit that allows us to control this LED with this little switch. It's thrilling. It's absolutely amazing. We can also press this button, which turns this LED on when we press it. It's incredible. But seriously, we are working here on a series of building an 8-bit computer. I'm following the video series by Ben Eder. He has a YouTube channel explaining a lot about computers, and he has this series on building an 8-bit breadboard computer. So on these breadboards, on these prototyping boards, building a whole computer. And this is the clock module. So this is providing the clock for the CPU that we are building. So this is, for example, a clock signal that we can control the speed of. And what we are building now are other components of this clock that helps us to debug and play around with this computer better. So we have the automatic clock here, but we also want like a clock that we can just advance ourselves by clicking, and then we can like watch slowly the CPU executing it based on our clicks. And now we added this switch which will be used to switch between the automatic clock and our button clock. So that is the purpose of this switch. And this was the third video of the series. Oh, Adam, also thanks for the cheer. Let's see. Don't forget the power LED on the top. Oh yeah, we should add maybe an LED that indicates if the board has power. That seems, if that's what you mean, yeah, we should do that. The interface in air is bad enough. Could switch on the capacitive lamp in my parents' room though. Wait, what? Sorry, I didn't catch what you were talking about. Okay, cool. So we have been streaming for over an hour. I think we can definitely head into the second video as well. Let's see. Oh yeah, I wanted to check if I have a different switch than this janky one here. Let's see. I have some switches in here. Here some switches. These are dip switches. Maybe this one here. We would have to solder this on something else. This wouldn't fit in a breadboard, and these are way too thick. Oops. I mean, it will do for now, but maybe we can find a better switch some other time. I need to order a different potentiometer anyway, because this one is like so huge and long. It looks ridiculous. I want like a nice small one that also better fits on here. So I have to order some more parts anyway for that. Yeah, and these ones, yeah, they're way too thick. Yeah, I will order that some other time. I quite like the janky switch. It's quite sleek. Yeah, you're right. And also the potentiometer that I will order will also be blue with a white turning thing at the top. So I think it will also look quite matte. It will match. So yeah. Are you leaving? No. Okay. Same. Yeah, that's a great thing about Germany. Our infrastructure is so well that orders will come like directly in the next day. However, I will probably order from Reichelt, not from Conrad. Still better than the US though. Like because the US is so large, like it's typical that things need like 3 days, which sounds horrible to me. How can you live without Amazon Prime next day delivery or same day delivery with Amazon Prime now? I have exam tomorrow and have no motivation to study. What topic? What is the exam about? Okay.
In the last couple of videos, we.
Okay, let's watch the next episode, I think.
In the last couple of videos, we built our 555 A-stable timer, which is putting out this oscillating clock pulse. And we built a monostable 555 timer circuit, which gives us a debounced push button switch. So we can push this and we get a nice clean debounced logic output here. And then we built our...
Okay, your exam is on algorithms? Okay, I know. Algorithms might seem super dry and it's super annoying to study this now. You might have to do like O notations and whatever, and you feel like, why the crap do I need to learn all these different kind of algorithms? That's so stupid. But algorithms are super important when programming, and they seem dry now, but just imagine their applications, what they could be used for. You think like, why do I need to think about sorting algorithms or stuff? Like every programming language has already sorting implemented in their modules and libraries. I don't need to do this. That is true for basic programming, but when you get like, if you build more complex applications where you handle like masses of data that are like distributed systems, streaming data streams to like your machine or something like this, and then you need to implement very efficient ways to aggregate them and sort them and stuff like this. You might have to implement these algorithms yourself again, because you can't simply put this data into what is given to you by the frameworks already, because it's way more involved. And you not only do you need to consider the basic execution of the CPU, but you need to take into account how quickly are certain operations, like maybe the trade-off benefit between reading stuff off disk, how fast would the network be, how fast would the RAM be, and then you need to optimize these things. And so maybe one algorithm, given that the network is very slow, would be better, even though theoretically in a perfect world would be worse. So just think of, if you are good at algorithms, you could implement crazy amazing applications later. And that's why you should learn a little bit this theoretical knowledge, because it will really help you later when you develop applications. And now go study. Okay, there. Sorry. Let's continue.
Bistable circuit here, which also gives us a nice, debounced stable output for our toggle switch. Now what we need to do is just combine these three signals here into a single clock output signal for our clock circuit. And what we want is we want to either output our oscillating signal or our manual signal, depending on which one we've selected over here. So I came up with a pretty simple circuit here that I think will do the trick. We've got our astable pulse input, which is this guy. We've got our select, which is the push button select. And then our manual pulse, of course, is the manual button that we can push there to get a manual pulse. And so what you see here is if our select is on, like this, then we have a 1 coming into this AND gate. And so our oscillator here, our astable oscillator, if it's a 1 or a 0, then that's just going to come out on this output here, because a 1 and a 1 is a 1, and a 0 and a 1 is a 0. So that's just going to pass through. And then it's going to come down to this OR gate. And well, first, if we look at this other AND gate, our select here is inverted. And so we have a 0 coming into this AND gate. And so no matter what this is, this AND gate's always going to output a 0. So then over at this OR gate, we've got our clock pulse over here on this one input, and then we've got a 0 on this other output. So again, that clock pulse just flows right through. So if our select is on, then our output over here is going to be our clock pulse. If we turn the select off, then of course we have a 0 coming in here, and our clock pulse isn't going to come out. This AND gate's always just going to output a 0. On the other hand, our select, when we invert it here, we have a 1 here, and so if our manual pulse is a 1, then we get a 1 out on the other side. If our manual pulse is a 0, then we get a 0 out on the other side. And the same thing with the OR gate. If we have a 0 or a 1 coming in here, we get a 0 or a 1 coming out here. This, of course, is always a 0. And so if we push our manual pulse, then we should see the manual pulse come out there when our select is off. So this looks like it should do everything we want. There's one other feature that I'm going to add to this, which is this halt line. And what this is once we build the rest of the computer, we want to have a way for a program to be able to halt the computer programmatically. So maybe you have a program that computes something, and it gets to the end of the program, it outputs its result, and then it doesn't have any more work to do, and so it wants to halt the execution of the computer. There's nothing else to do. So what we'll have is we'll have a signal coming from the control module in the computer coming into the clock. So it'll just be another input into this clock circuit that says halt. And what that does is it should just turn off the clock. And so if there's no clock, then the computer's not going to do anything. And so what happens is we have this halt signal come in. It's normally going to be low, and so we invert it and get a 1. And then that 1 is just ANDed with our clock before, whether it's manual or the automatic clock. It's ANDed with that, and it comes out here. But when the halt goes high, if the program wants to halt execution, this goes high, then this goes low, and then you can see the final output over here of our AND gate is always going to be a 0. And so there will be no clock, no matter whether you've got it in manual mode or using the oscillator, pushing the button. It doesn't matter. You're going to get nothing out there until we reset the computer, or restart the program or something. So if we want to build this up, it looks like we've got a couple inverters, 3 AND gates, and an OR gate. So what we could do is we could use the 74LS04. This has 6 inverters on it. Of course, we're only going to use 2 of them. We've got the 74LS08, and this has 4 AND gates on it. We're going to use 3 of those. And then the 74LS32, and this has 4 OR gates on it. Of course, we're only going to use 1 of them. A little bit inefficient to use these 3 chips. We're not using all 6 of these. We're not using all 4 of these. We're not using all 4 of these, but it should work. And one thing we could do is we could redraw this using different gates. For example, you could use all NAND gates or all NOR gates. Any logic circuit can be represented entirely in NAND gates, or it could be represented entirely in NOR gates. Those are called universal gates. And so just an example, I drew up an equivalent circuit here using just NAND gates. And so these are the same inputs. We've got our astable pulse, our select, our manual pulse, and then our halt line coming in. And I'm using just NAND gates. And so, for example, this NAND gate, I just tied the inputs together, and it turns it into essentially an inverter. And so the nice thing about this is that by using all NAND gates, it looks like we've got 1, 2, 3, 4, 5, 6, 7 gates total, 7 NAND gates. And so the 74LS00 chip has 4 NAND gates on it. So we could use just 2 of these. And so normally this would be a pretty good win here, right? We're using fewer parts, so it's going to take up less space, it's going to take less power, and it's going to be smaller and everything else. But you know, we're not building. We're definitely not trying to optimize for the smallest computer possible here. And I think this circuit is easier to understand. It's going to be easier to troubleshoot. We're not trying to save space. We're not trying to save power. You know, the cost of an extra chip is, you know, less than a, you know, it's good. It's a, you know, 50 cents or something. I don't know, whatever these chips cost. And so it's not a big deal. So I'm gonna use these just because I think this circuit's easier to understand. But if you want to, you know, experiment with something else, you can. And actually, if you want to try to come up with a better circuit here, I didn't spend a whole lot of time on this, and I got it down to 7 gates. But maybe you can do better. So maybe something to think about. Okay, so I wired it all up here. So we've got our 74LS04, our 74LS08, and our 74LS32 all hooked up here. And you can see I hooked up the power pin to pin 14 and the ground to pin 8 or pin 7 for all of these. And that's how they all are. If we look at the data sheet for the 74LS04, for example, you can see power pin's 14, ground is pin 7, and it's got the 6 inverters on there. We're only using 2 of them. And then the same thing for our AND gate. This is the 74LS08, and you can see it's got power and ground, and then it's got the 3 AND gates, or excuse me, the 4 AND gates. We're only using 3 of them on there. So if we kind of follow this through just to make sure it all looks right, the output of our select here, so when we push our select button, that output, of course, is on pin 3. That's connecting to our input of our inverter, and then it's also jumpered over here to the input of one of our AND gates. So that looks right. Select is going to our inverter and one of our AND gates. The other input of that AND gate should be our astable pulse. And so indeed, that was this AND gate here. The other input is this, and it's going all the way over to the output here of our astable pulse on pin 3 of this 555 timer. So that's our first AND gate. That looks good, and our first inverter. The other output of that inverter goes to another AND gate. So the output of that inverter is here, and that goes to an input of our second AND gate. And the other input of that AND gate is this guy here, so that comes from the output of our manual pulse. So indeed, the manual pulse goes in that second AND gate. And then the outputs of both of these AND gates should go into our OR gate. So the outputs are here and here. So here is going into pin 1 of our OR gate, and then our other output is here, and that's going into pin 2 of our OR gate. Perfect. And then the output of our OR gate comes around to the input of the third AND gate, which is up here, which is what we'd expect. And then the other input of that AND gate comes from this inverter that comes from our halt signal. So if we follow that around, the other input is coming from an inverter, and I'm just using one of the other inverters on the 7404 up here. And then the input of that inverter is coming from our halt pin, which I've just jumpered here to ground, since we don't want to halt. And then the output of that AND gate is our clock signal. So I have this nice blue LED showing us what our final clock signal looks like. So let's take a look at this. Let's plug our power in, and nothing happens, but that's because we should be looking at our manual. So if we pulse our manual, we see the manual output. If we turn our select on, we're now getting our clock output going through there, and we can turn that off, go manual. If we have that, our manual didn't do anything. And then if we unground our halt and put that to 5 volts, it halts it. It doesn't matter what we do here, the clock output's halted. So if the computer program that's running wants to halt the computer, it can do that by bringing this halt line high. So we'll just leave that low for now. We can see it looks like it does everything we want it to do. And so the last thing I'm going to do on this before we call the clock module done is I don't think we need these LEDs anymore. I think the clock module is pretty simple by itself, and just seeing the final clock output makes sense. But you might want to leave these other LEDs here if you want. But I'm gonna take them out, and then of course we can take out the resistors here as well. I guess I could take the power off while I'm doing this. So just pull these LEDs and resistors, the current limiting resistors for these LEDs out. And that leaves us with this. And so this is going to be our finished clock module. Plug the power back in so we can see, we can run it, we can stop it, we can pulse it, and if the computer halts it, then it doesn't matter what we do, it's halted. And so that's the clock module. So in previous videos, we've looked at the OR gate, which if you remember, in this case, if we have two inputs, if one input or the other.
More LEDs are always better. Yeah, it was hurtful to see him rip out all those LEDs. That's blasphemy. Wait, there was some... Yeah, sorry for removing my picture in the corner. I saw it too late, I think.
The other, or
but I hope you got
videos.
the block diagram. No, that's basically it here. Use color changing RGB LEDs. Yeah, that would be funny. I definitely need a different switch. Like switching that is not so nice. I want the one that Benita is using. That one is great. Okay. Yeah. Let's see. Okay, so I think if you watch this video, you get what these black magical chips are. I think like this is kind of like a learning experience for me. You know, for the first time when I did like electronics, you always look at like PCBs and you see these black chips and they are so mysterious. Like what are they about? Like what's in them? And so understanding that you know, in this case, for example, this 3 shown here on in Benita's videos, 3 laying there on the paper, they are just chips that implement different gates. So they just have this transistor logic in there to implement an AND or an OR. And there's nothing really crazy about them. That's just what they do. Make a custom-made module for those AND OR gates. Like, wait, what do you mean? Like with transistors, building it yourself? But yeah, maybe we could like also find in the store. I'm sure there are chips where like there are, I don't know, 2 AND gates or on it and 2 OR gates or 3 ANDs and like a certain combination. I need to go shopping anyway. Like I thought about like ordering again, but I figured for just a few simple parts, ordering right away is a little bit unnecessary. It's not like I need it urgently. So I kind of want to collect a few things that I might need, and then I place the order. So for the potentiometer, a different switch, and stuff like that. And then I might also look for different ICs here just for practice as well. I think that would be could be cool. Yeah, FPGAs are interesting. I mean, I also have only done like the basic, but yeah, the software is hard to understand at the start, and yeah. So let's see. I need to find the chip numbers exactly again of these. Okay, so the AND gates are 7-4. Okay, so we need the 08, 32, and was it inverter? The 04? I think he also wait. I think oh crap, wrong button. No, wrong button. Wait, I'm confused. Oh no. Let's see. I think when you go onto the clock module here, he was listing again which chips he used. Yeah, the hex inverters. Okay, 04, 08, and 32. Let's see. Usually only one type of gate on a simple chip. Okay. I mean, I don't know. It could be maybe that they don't do that. I could imagine that they have also chips that are like mixed, but might as well not be. I don't know. Okay, so here we have the 04. Uh, 8 and 32. Oh, 8. Those are the AND gates. John, Steve, are you buying some parts now too, or what? And the 32. Wait. 8. Wait, what? 4. Where did I put the 4? Am I stupid? Oh, these were in here. I'm stupid, yeah. 32. I'm looking for 32. There we go. There we go, 32. Why is everyone hating on VHDL? I mean, I don't have much FPGA experience. I basically did 2 small toy things. And by toy, I mean like a blinking LED basically. And I did Verilog and VHDL. I did really like VHDL. I think Verilog looked a little bit simpler, but I was starting with VHDL and then moving from Verilog. So Verilog felt very comfortable coming from a little bit more verbose VHDL. But yeah, I don't know. I did not buy the kit because of super high shipping from the US for his kit and possibly also VAT or duty stuff when I'm importing it. So I would have ordered if I was in the US, so I ordered the single parts. I ordered them from a German store mostly, except the breadboards and these wires. I imported those from a US store because I can't find them in a German store. I ranted about this yesterday. We made a virtual washing machine in VHDL in school. So, like, I understand like the basics of FPGA. I have a video where I used an FPGA for a CTF one time. But what I really would like to do, and I've never done that, is basically you know like the cool thing about these FPGAs is that there are these components that you can just like buy, or they are for free or something, or you take them from other people that made them. So for example, you can, and that's the thing, like the easy language is you can just take that block of like an Ethernet or a PCI Express block or something like this, and then you build a custom thing on top of that. And it always sounds so simple. You just take this block and this block, you put them together and connect them, and then magically you have this amazing application. But in practice, it seems a bit harder than that. But yeah, that's the thing I would like to do. For example, people were using FPGAs to attack the the MacBooks. Like the Thunderbolt or something was basically exposed PCI Express or something like that, and PCI Express supports direct memory access DMA, and so by using that you could just you had control of the whole memory of the machine. So basically if you plug in anything in that port, you could just take over that computer. And so people were like doing presentations on that, and they were like saying they just simply used an FPGA, and then they used like a PCI Express module, and they they pulled it together and had this proof of concept ready. And that seems so crazy to me. So I wish I would be able to do that too. I ordered on Reichert. I made like my parts list with links to where I bought them. I wanted to clean that up and share it as well. If you send me an email, I can send you the link right now. It's just not cleaned up for like publicly releasing it. Yeah, I still have the order list. Can you also write me an email or write me somewhere, and then I can just share the list with you? Okay, so I guess maybe that's a practice, and let's work based on this schematic here instead. Ooh. Sauerkraut Slack, yeah, you can write me there, perfect. Okay. So let's plug that out, and then we start with, so the 0.8 was the AND gate, right? Okay, so let's see, 0.8, 0.4 was the inverter, and we have the 32, which is the OR gate. When you finish, make a PCB out of the design. Yeah, that's another thing. I'm sure people have actually done that already, and that actually would be cool to have like a big board and you solder it and it blinks and you can kind of rearrange that. That would be also kind of a cool project. Yeah, I kind of like that idea. Okay, so we could put that here. I have a little bit of a space problem because I put the wiring down here. Benito had it on the other side, but our huge potentiometer is in the way. Hey, didn't know you streamed on Twitch. I just started. Like, that's the third stream, basically. I mean, I have on and off streamed sometime, but I haven't done it for a while. I guess it's time to sacrifice these for now down here, because maybe I can fit them nicely in somewhere else. How does it look? It looked kind of weird, but whatever. For now, it's okay, I think. You could use a SMB component. Yeah, that would be really cool. I think that would actually look really nice. Somebody must have done that already. I might try to search for that later, like the Ben Eater on a PCB. That would look so cool. But then you would want to do the design with more memory and maybe more instructions and registers that you can run something really cool on it. Maybe also, more registers that would, or like a graphic unit that allows you to control like a small LCD screen or something like that. Yeah, I think that would look really cool. Or even if it's like larger, you could like really, arrange it beautifully. Like if it was as big as like this thing here, I think it would look really cool. Why is your energy so low? What are you talking about? I'm like really trying to be more active. It's really straining. Don't put multiple loose boards in one panel though, they will bill you extra. Wait, what do you mean? You just seem tired, man? Oh man, okay, wait. I feel like okay, maybe I don't know what to tell you. Like, I'm way more upbeat right now. I really try to be like really active. In real life, I'm even a bit more chill than that. So if that's if that is low energy to you, then watch yesterday's streams. I think like today I really try to be a bit more. I checked out like my own stream yesterday and felt like I was a little bit too weak to be entertaining for Twitch. So I really try to be a bit more on it today. But I guess it's not working. If you want to become serious, don't use ego. Okay, so let's put that in here. Yeah, like that I think would be good. Oh, that's so satisfying. So I don't know if those were now a good order, but we will see. Just don't plug those LEDs out. Okay, so so which one is which? So in the front we have the AND gates. We need to look up the data sheet as well, that we know which port is which. Let's see. Did he link the schematic directly here? Perfect. Okay, so we start with the AND gates, which is 0, 8. And this is the diagram. Okay, so, and we are connecting. So the first AND connection is three from the switch and 3 from the clock at the start. Oh wow, that's becoming ugly. Okay, so we need to connect pin 3 with for example, crap, what's the orientation of this chip? I guess 1 and 2. So 1. Okay, let's cut here. Okay, so 3 up here. Okay, wait. Now this does become a little bit ugly here. Oh man. Let me use jumper wires for now for this bridge connection. Pin 3 is connecting with pin 1. Crap. If I make a pretty bend like this to make it like aligned nicer, then it's a bit too short. Will you apply for a job at Intel after this? I don't think so. Wait, what's about smart contracts? Country writing at school. Oh, the Ethereum smart contracts. I never really understood smart contracts. Yeah, that's also like a to-do on my videos, like that I would like to make videos about at some point, like some smart contract tutorials or something like this. Not because I'm not into. I feel like I need to always say this disclaimer. Like, I'm not interested in cryptocurrencies at all, and I think most smart contract stuff is all scam, or everything is a scam basically. But I do find smart contracts from just like a computational standpoint, from like a computer science standpoint, really fun. Like the same way we are building a stupid 8-bit CPU to execute some stupid instructions. I think it's fun to see like a smart contract execute instructions on the blockchain. It's just a weird. Oh fuck. Oh my god. It's just a weird execution environment, which is kind of fun. I really need that wire stripper. What do you love about Ethereum, like this idea? I still lack good examples of applications for blockchain or smart contracts specifically. didn't get the real use case for smart contracts. They just did for everything because it's a buzzword. The sad thing about the 8-bit computer is that you don't have that much programming memory. Yeah, but there are people that did like extensions to it, and they modified it to have like a lot more RAM, like 256 or even a kilobyte of RAM. And so eventually I also wanna, like, once we understand how this whole computer like works, that's also one of the modification that I definitely wanna make. Okay, nice. Finally. Well, basically the fact that it is transparent, so everyone can prove that you did a certain transaction or own a certain token. I mean, there are other ways to prove that as well, I know. You can't do gambling on a smart contract though, because it has to be fully deterministic. There's no randomness. Make an exclusive club with smart contract. What does that mean? Okay, so we connected the first end, and now the second one is connected to the 3 output of the switch. So in this we go to B. Make an exclusive club with smart contracts for live overflow viewers. I have no clue what you're talking about or what you mean. What does that mean? There's no randomness, but you can't really know at which point your code will be executed. Therefore, you could include certain that in the hash, which make it unpredictable. No, well, that's the thing, you know, like that's true that it kind of makes it a bit hard, but in the end, it's like not cryptographically great. Like, right, the miner that finds a block and decides to include that execution in the transaction or not knows the hash and can decide if it will execute that or not. And if that miner is participating in the gambling, the miner can check, would I win with that hash? Nope. Then let me not include it. Please stop about the smart contracts. I mean, so for example, what bothers me the most with a lot of the blockchain smart contract stuff is that first and foremost, they sell it in their marketing material as this amazing like technology, right? And so the main focus should be on developers, like explaining the technology, how to implement it, good example applications, stuff like this, right? And then you go on these blockchain websites that explain their new blockchain technology. And there's a lot of marketing blah blah, how their blockchain is so fast and how their smart contract system is so much better and that it solves all these problems that the other blockchains have and it's all magical. And then they have a technical paper and they have a white paper and you read it and there's just literally no technical information in it. It's like high level abstract bullshit, no actual details, and that just tells me everything. So we connected these two. Awesome. Now do it like GeoHut. If anybody talks about smart contracts, you're gonna get a time what. Well, as long as we are ranting about smart contracts, it's fine, I think. Making progress so far? Yeah, kind of. We implemented this button today, so we finished one whole video, and we're actually working on a second video today. So trying to finish this one up. So it's Ben Eater's version. Why is it? Oh. The fourth video in the series. Oh, and if you have just joined, look, I changed the whole setup. Isn't this? It's so much better to work on now. Okay, so this output here of the switch now also has to go into the inverter. Well, do we deal with that inverter? Let's first connect this output with the second AND gate. So this third one here has to go into the second AND gate. Let's see. So we could connect it to the fourth one there. Here, 1, 2, 3, 4 here, and then so we can cut here. Oh, what was the question? I'm sorry, I have no dumb question, but what is an 8-bit computer? Yeah, so it's like, yeah, okay. The answers, the people that answered, yeah, was exactly that. It's a computer that uses 8 bits of addressing, basically. It's based on the video series from Ben Eater. I'm sure somebody will link it or something. What's the schedule for today? Around 3 hours. I mean, ideally, actually, I want these streams to be shorter than 3 hours. Actually, I'm hoping to be kind of more at like 2 hour because otherwise I will not be able to keep that up consistently. It's just too long. But I guess I will always make it dependent on how the progress is going. Like I always want to have kind of like a milestone, I think. And so far it has always worked out kind of about 3 hours with these videos. And we finished already one videos in the first 1.5 hours. So I decided to tackle this next one. So I want to finish now this video as well. And then, so yeah, so it should definitely be, I hope we can finish this within the next hour. Okay, so this was here, going to the 4th pin like so. Nice. Joshua. Okay. And so now the other input for the AND gate would be the output of the inverter coming from the switch here. So I guess we do the inverter here. How did Ben arrange this nicer? Okay, so this output could go to the inverter. So which one was the inverter chip? Inverter was the 04. That's this one here, the second one. What are you using as transistors to build logic gates? We are not using transistors to build the logic gates. We are using logic gates implemented in these ICs. So this one includes like 6 AND gates or so. Here are inverters, and here are OR gates in it. So we need the data sheet of the inverter. Like here, this is the data sheet of the inverter chip here. So pin 1 and 2, we wanna get a wire from here to cut here. What am I currently doing? We are following the Ben Eater series on building an 8-bit computer. And right now we are working on the clock module of that computer. So the part that will generate the clock signal for the computer. And this clock module is built in a way that it has the regular clock and also a debug clock where we can like control with a button, always press to advance the clock. And we are building like the circuit around it now that combines these 2 different parts to be switchable with a switch, so we can select our button press clock or the automatic clock. That's what we are building right now. Okay, so the switch output 3 goes to one end and goes to the inverter, and the output of the inverter is here pin 2, and that has to go now up there. What part are you currently doing? That's the clock module. Let's check again the AND gate. Oh, it has to be connected So 4 and 5. 1, 2, 3, 4 is one, and 5 is the other one. And 5 from here. And then the inverter is on to the output. So okay. Cut off a bit more here and then strip from here. I really need a wire stripper. I keep accidentally damaging the core a little bit and I worry that I might break them at some point. What is the maximum speed? That's actually a good question. When we have finished setting this up, I actually want to measure the maximum hertz that this clock module runs at. We actually don't know right now. Or I don't know. It's also selectable, the speed based with this potentiometer here, but still I don't know what we can select as the maximum speed there. Okay. So we have finished setting up the first stage here, both these two ANDs and this inverter beforehand. So now these outputs here, so that would be pin 3 and 6. 3 and 6 have to go into the OR gate down here. And the OR gate also, I assume, yeah, also just pin 1 and 2. So 3 and 6 as outputs going into 1 and 2 down here. So we could go from here down like that into 1. Oh. Thanks Intel Pentium 4 for the sub. You are definitely faster than this 8-bit CPU that we are building. And the Weed Panic, thanks for the bits. You made this for a school project and it took me so long. Don't be intimidated by the wiring now, it gets much worse near the end. Yeah. Well, I don't mind if it takes a while. I'm kind of looking forward to it, to be honest. Oh crap, I pulled out the... Oh, let's cut this again. Kind of looking forward to it, to be honest. It seems like, I feel like if I would do just that alone, like just sitting here, I might give up on it. And so I'm using streaming as like a way to pressure me into keep going with it. In the current configuration with the potentiometer to 0, it can maximally run 480 Hertz. All right. Any 55 claim 500 kilohertz. Yeah, but I'm not sure with the configuration how it is set up. One, two, three, going down there. Okay, so that is the first AND gate connected, and now the second one. So this has to go from 1, 2, 3, 4, 5, 6. So from here from here, no, wait. Here to might be a bit short. Let's see. What is your goal with this project? Yeah, just to build it. It's an 8-bit computer. It's you know, to learn more about electronics, and you know, I have somewhat of an understanding of how a computer works, but actually seeing every single component, because there are a few parts that are still a little bit confusing to me, especially like the execution of like instructions, and how the bus works. I mean, it's not, you know, not quite as complex as modern CPUs do it. It's a simplified version. It's literally, it's based on the architecture of SPA, simple, or SAP, simple as possible CPU. And so, so I hope to get a better understanding, to learn more about electronics, and just to have fun, you know. I don't know. Okay, so now we should have also connected the OR gate. Hit me up if stuff confuses you too much. I have a working one. Nice. Yeah, will do. I don't. Twitch auto-moderated the term cable stripper for obvious reasons. Yeah, I know. I put it on. It's on my. I ordered it from Amazon. Maybe it comes on. Not from Amazon. I ordered it. Where did I order? I ordered it from somewhere. I hope it arrives tomorrow, but maybe the day after tomorrow. You know, but practicing stripping cables with just a clipper is maybe also a skill you need. I don't know. Okay, and now this feeds into the OR gate. So the output of the OR is also 3, and that feeds into an OR gate all the way up there. Okay, so maybe we can, so we need to now use, so that's the OR gate, right? Wait, oh no, an AND. Oh, I'm sorry, it's an AND, not an OR. That's an AND. Okay, so this OR output has to go into this AND up there. So we take pin 3 from here and have to wire it up on the other side now. So for example, pin 13 or pin 12 up there. So like this, bent around the curve like this, and then going up there like this. But you also have to program, can you like program using some dip switches as far as I remember? Yeah, but you also have to program the EEPROM to make it run, but either write some program for the Arduino. Yeah, I saw that. Definitely also gonna do that when we reach that. But for example, I haven't watched the series completely yet. I just, picked up a few pieces here and there. And so I don't, for example, know yet the purpose of the EEPROM. But don't spoil, we will learn about it soon enough. How much RAM does it have? 16 bytes. Yes, it has. It's not a joke. It has 16 bytes. Theoretically, it has an 8-bit bus, I think. So you would think maybe it can address 256 bytes, but as far as I understand, the instruction set that Ben Eater implements is so basic that he only uses 4 bits in the instruction encoding for addressing, which only allows him to access 4 bits worth of addresses, so 16 bytes. But people have created extensions or different instruction sets. So I don't know exactly how that works yet. So we will figure that out once we get there. This, and then we bent it here. And then we put it, I guess, in here. Come on. 3 and 1. Oh, wait. I'm 1 pin too far. It goes in here. Oh, no. All the way. So pin 14 up there is the VCC. Which obviously is 1 pin too far. There we go. I was just gone for 10 minutes. What do you mean? Welcome back. Okay, there we go. That looks nice, I think. I was gone for 10 minutes. I want to know what happened so far. Well, where did you left off? I don't know what 10 minutes ago was. We are still working on these chips here. Okay, so and now the second one in here, the second input is the halt. So that's the halt input. So I don't think we care about this much right now, but let me get some jumper wire. So first of all, we need, and should maybe put that back on, the connection for plus and minus. And so this is the halt input. Oh wait, the halt input is also inverted first. So we need to go from the, wait, this was the inverter. So from here, we have a halt input, which could be, for example, here. I think we need to check, and then we move another wire up there. So yeah, this would be input, and then this would be output. Okay. Can you do an automatic jumper, like press a button to halt instead of disconnecting? Yes, basically that's what we have here, right? Like this is the automatic clock up here, and this is our clock with the button press. So as soon as we change this, that's what we are building right now, right? That you can select between the automatic clock and the one we click. So if we switch from the automatic clock to our where we click, boom, now it would halt, and it would wait for our button click. The halt line here that Ben Eater added there as well is additionally, there's another input that can completely halt the CPU. And as he mentioned, this will be later be implemented as an instruction, so that there will be a halt instruction that will just halt the whole CPU by changing this here. So this is just an additional halt, but if effectively we can also execute a halt by just changing to the manual clock input. Okay, so we move, yeah. From here. Okay. Why does he not use a jumper instruction to the current program counter and the loop to stop the thing? I'm not sure. I mean, that is certainly possible, I guess. Just a different way to halt, I guess. It might be simple just to have a halt instruction versus jumping. I think jumping is probably pretty complicated instruction compared to a simple halt, maybe. Maybe you just want to recognize a proper stop. Okay, so wait, what am I doing? So this is the input, this is the output, and this goes up to here. Was that it? Okay, let's trace this really quick. Let me see. Let me make that a bit larger here, and then we quickly verify. And I know that we still need to do the power. We still need to connect the power. But Okay, so that's good enough. So let's see. We have, I need a pointy device. Oh, yeah, I guess this will work. Okay, so up here you can't see it right now, but there's this long wire going down. This is going as an input in one AND gate. The second input of that one, this pin, has to be the switch, correct? Now this switch output also goes into the inverter down here, and this output then goes into an OR gate here. Wait, that's weird. Oh yeah, no, here, OR gate, okay. And the other input of this OR gate wait, what am I? No, sorry, ignore me. The switch input goes down here into the inverter, and the inverter output goes up into the AND gate right here. And the other input of that's the bottom AND gate we're talking about right now, has another input, and that is the click the button input. So this is this one going up there. And then that output from here, so that would be this one here, goes down to the OR gate as an input. The second AND output here goes also down there, and that output then goes into the other AND, which has the other input to be the inverter coming from halt. So this is halt being inverted going up there, and that is an AND that has an output here, and that will be our LED. Okay, so now we need to hook up the VCC and ground and the LED, and then we should be able to test it. You should probably remove the overlay. Sorry, whatever, we're done. You don't need it so big. I thought I'd make it big enough so you can see the tiny connections too. You forgot to add VC. Yeah, I know. I will do that in a moment. What is the inverters for, please? The inverters are simply inverting. So from plus 5 volt, if there's a plus 5 volt signal, they do it 0, or if it's 0, they do it plus. The reason why they are needed is just that, an AND, you might want to have an inverted input at the AND gate. It's just, sometimes you just need the inverted value, and so you need a gate for that. Come on, look at your screen. Chill, dude. Chill. Relax. But thank you for looking out for me. Okay, so the connections I think all had the same. VCC was pin 14 and ground was pin 7. I think they all had that in common. Yeah, okay, so we need... Don't be sorry, it's fine, don't worry. Okay, so VCC connected for the first chip. Ah crap, I should have measured the length. Oh my god. Oops. I'm alive. I'm okay. I kicked over my trash can. Oops, that was way too long. Oh, what am I doing? Oh my god. Didn't you hook up GNZ? Yes, I did. Oh man. What an idiot. So 14 up here. Oh my god. Okay, so there we go. My mistake was using a PC power supply to power it at first because I didn't have anything else. That was almost a dead chip. Oh man. Yeah. We had some short circuits last time, but luckily I have here the like a power supply with limiting current. I'm not sure what I set it to, but maybe we could have been fine. I'm not sure. We could have been lucky. So far we haven't seen magic smoke. Okay, and now down here. Yeah, but a PC power supply is very different. I would have just hooked up the wrong direction with 5 volt, but you with a PC power supply you would have like 12 volt. Oh, PC power supplies have a 5 volt rail too? Oh. Then what was the issue? Or did you also had like wrong connections that burned up? So this is G and D. Wrong wires. Okay. Were you trying to overclock it? That's one thing that I kind of want to try out. Like if we can glitch the CPU with a much higher clock rate, like when it's all set up, like when it's all working and stuff like this, and we can actually write a bit more code, we have a loop, and then I wonder if we can glitch it to break out of that loop, like as an attack. That would be kind of cool, I think. We should try that, and maybe we can like observe this, you know, like we can maybe we find a good point where we can measure with the oscilloscope and see basically when the glitch happened and why it happened or something. Oh my gosh, it is connected to pin 6. Thanks so much. Jet has really good eyes right now. Amazing. I feel so confident about this build now because I easily make stupid mistakes like this, and so that you notice is very valuable. Okay, and now we only need to have the output. So we need a blue LED. Do I have blue LEDs? Did I order clear blue ones? That's sad. I guess whatever. The ground is wrong still. Oh god. The other one too. No, no, it's correct. I think it just looks that way. I think what I need is to have like a smoke detector that is connected to some alarm wires, and if we ever trigger the magic smoke in this build, then we could have like this amazing light show. I think that would be cool. Yeah, the wire was shifted weird. I think it might be shifted up a bit. A fire alarm emote maybe would also be fitting. Okay, so the output of this one up here would be the clock. How did Ben hook that up with the? Where did he place the resistor and stuff? Oh, he just hooked it up directly without a resistor? Naughty boy. He was also doing a negative clock signal going down again as well into the inverter. What is the demand of this 8-bit PC? I'm not sure what do you mean with the demand. There's no demand. The demand is I want to build it. Okay, so maybe we could move it down here and then have a resistor going over like that. Or I could do the resistor here and have the LED go over like that. Maybe we do it that way. Okay, like that. I dropped something. Okay, so we can put the LED crap. Here, and then we can connect a resistor going from the output here down there. Oh yeah, I know about the teleportation of stuff, of electronic devices on the floor. I mean, that's what you get if you work with magic. You know, sometimes your magic smoke escapes. Sometimes the aliens take your components back. That just comes with the topic. Okay, so now we have the resistor for the LED, and now this output also has to go into the inverter for the inverted clock. So we need a wire going from here to here. So from here to here. Oh, damn. Reminded me again of the uptime, almost 3 hours again. God damn it. I guess if you enjoy streaming, it's not that big of an issue. Sure, of course I enjoy it. It's just like time-wise, you know, I have other stuff to do, unfortunately. You know, if I would get filthy rich from just doing this, you would see me here 8 more hours. And then we have the inverted output down here. Okay. I kind of just want to plug it in now and see if it works. Are you ready? Oh my gosh. Okay. Everybody ready? It could blow up, so pay attention. Here, let's get the screen out of the way. I take safety. Okay, something is wrong. This LED should not stay consistently on. Let me move that switch. No, wait. Oh, sorry. No, this LED. Sorry, I'm confused. This LED was the switch, but clearly this output is not working. Okay, so nothing is blowing up. This means we can debug it at least. Connect the hold line. Oh, do we need to connect that? Wait, the hold line should be connected to plus, right? To VCC. No, to ground, because then it will be inverted. I installed an IR light. Yeah. Okay, cool. So it's blinking according to the clock. Nice. Okay, now we do the switch. It's off. It works. Now it's our button press. We put it back and we have the clock. We put it here, button press, and clock. The camera would see the IR. I'm not sure if that might, a lot of cameras have IR filters also, but yeah, we should have noticed it, I guess. Okay, let's, then I would say we just quickly hook up the oscilloscope, and also I want to measure the speed. I would also be curious if we can see a delay of propagation from the original LED blinking to blinking down here. I wonder if going through all these logic gates, if there's like, if that takes, no, can we measure that? Probably not. No, that doesn't make sense. We probably can't measure their difference. Like the speed of the switching transistors. Maybe, I don't know. Maybe this is a dumb measurement. We will see. The propagation delay is in a, yeah, okay, yeah, you might be correct. Okay, so let's turn on the oscilloscope. Let me place this here. And then, okay, so what do we measure first? Let's measure the speed first. So we hook up ground and we go here to the output. I guess we can measure it from down here. There we go. Let's make it a bit faster. There we go. There's a lot of noise. So ignore the blue one. Let's disable that. But cool. There we have our clock signal. Is that noisy? Does that look bad? Alright. Damn, already wanted to finish watching in bed, but want to keep seeing the measurement more clearly. That's fine? Okay, cool. Okay, so let's see. We have the, let's move the, okay. So currently we run at 18 Hertz. So let's turn up. Oh, that quickly jumps. See how we can increase here the speed or decrease it. Okay, so let's see. This is 200 Hertz. So we have here the measurement screen. It's too small for the stream, but here is a frequency calculation. So it shows here the frequency that it measures. And so currently it's 300 Hertz. 380 Hertz, 500 Hertz. Okay, 500 Hertz is the maximum. It is running with 500 Hertz. I hope I can do everyday streaming, so tomorrow. What are you trying to build? We are following Ben Eater's series on building an 8-bit computer. So this is the clock module that we built. This is the clock for the computer, and I guess we've just finished the clock module. And so we are measuring right now the clock signal. So you can see here the nice square wave of high, low, high, low, high. 0, 1, 0, 1, 0, 1 of the clock signal for the CPU, which we can adjust the speed because it's our own CPU, so we can debug this. So now we can also, switch. Oh, I know, well, that doesn't make sense to measure. Let me quickly move over, plug in the second one to check if the inverted clock also works. We haven't tested that yet, but we should see this here easily with the second probe. So let me turn that on. We don't see anything. Great. Oh, wait. Is that maybe not quite in? Let me check the schematic of the inverter. It should go from 13 to 12. It has like a weird level too. No X-tau clock more stable. Sorry, I don't know what X-tau clock means. The LED pulsing because of the shut. Oh yeah, true. Wow, that's cool. It's actually super fast. Right now it's 30 Hertz, 30 times per second, but the pulsing. So I almost matched the FPS rate, but not quite, so it was pulsing slowly. That's 34 Hertz right now, so it's a crystal. Well, the problem is with the crystal. Crystals are super fast. I don't know what the minimum frequency of a crystal is, but we want to see the CPU slowly executing. We want to see each clock cycle slowly. That's why there is even a switch on here that allows us to switch to a mode where we can, with our button click, just execute single clock cycles, because we really want to. Later you have like this whole, like the whole table will be full of breadboards with the different components of a CPU, and then we can see how how each cycle of the CPU is slowly executing our instructions. So that's the goal of this. That's why we are not using a crystal with like megahertz or thousands of hertz, but we want to actually go down to like visible, you know, like 2 hertz or so. How does a clock interact with the CPU? I mean, you can watch Ben series, but basically, well, it's the so it basically comes down to the flip-flops that I'm really not sure how to explain that. I'm also obviously not knowing it quite. That's also why I want to build this, you know, to understand it better. But how I imagine it right now, or how I think about it, is that a lot of these electronic components, like in flip-flops, they might react on like a rising edge to set a certain state, and that state can then slowly propagate always, and that state can like influence the next state and stuff like this. And the clock with the rising edge always tells the circuit to now set the output. You have something on the input waiting for the rising edge, boom, set the output. Next clock cycle, set the output. And then you have a lot of logic gates, and then each rising edge, the state is propagated one forward. That's how I imagine it, but I'm not sure. Also, my understanding, again, the reason why I want to build this is to understand it better. But as far as I know, a single clock cycle or a single clock tick is also not executing a single instruction, because instructions require multiple cycles to be executed. In modern CPUs, it's very complicated, but in this basic CPU, as far as I understand, we have a defined row of cycles, and it might be like the first cycle we fetch the instruction, the second cycle we kind of like decode it or something like this, in the third cycle we, I don't know, set the register values, the fourth cycle will check if flags are being set, and I don't know, like something like this. In modern CPUs you have also pipelining, so you have you don't need to wait 8 clock cycles to fetch the next instruction. You can always use fetching in every cycle, and you will prefetch the next instruction already. So that you can parallelize it, and that's then pipelining, as far as I know. It's not spamming, it's alright. Maybe you don't need to post the same link many times, so it's okay. Maybe it will be nice to put some decoupling capacitor. I think actually we have one here for the bit on the power rails here. I think this is a 0.1 microfarad capacitor, if I remember correctly. Is that what a decoupler is? Sorry if that was not the case. Okay, wait, so what did I want to do? I wanted to understand why the inverting doesn't work. So let's look at this again. I mean, so the inverter must work because the rest of the circuit works. So the power supply is correct there. So why? Maybe is this not properly connected? No, wait. If we measure the clock cycle down here, so this definitely must go in. So why does it not show us the output on 12? Oh, wait. Do we need to... Can we not measure just the output here? Do we have to make a connection? Do we have to put like a pull-up resistor there? Is that the reason? Do we need to pull up resistor? Is that the correct term I'm learning on pin 12? Did Ben Eater do something? I don't know. Because right now there's like nothing that draws. My reasoning right now is that there's nothing on pin 12 that will consume the output. You know, like nothing will draw any current, so there's no voltage to measure. There's no electricity flowing at all because it is not connected. So we can't measure anything there. But if we put there a pull-up resistor, yeah, like a 1K resistor, we should be able to measure something. Is that correct? Or will I fry something if I do that now? Okay, I put there a 1K resistor. If it burns up, it's Pro GJ's fault and you will be banned. Wait, does it have... No, I have to connect it to ground, right? No, wait. Where do I want to connect it to? Okay. I pull up would be connecting it to plus, right? Oh wait, that's the wrong one. Okay, now it's just high. Was it wrong? Do I need to connect it to ground? Here it's just, okay, wait, this is consistently just high or consistency low. But I would assume you don't need it because it, that also makes sense. Okay, so why is the inverter not, should I try, wait. Let me check again. So the inverter is here. So I'm connecting to pin 13 and 12. Your channel 2 has a high impedance. Are you really measuring with the channel 2? Sorry, I don't know what you mean. Since you can pull the signal to VC or GND, you can assume it is in high ohm state and not driving the pin. This could be the case since the input is not connected to the correct pin. So the chip itself must have power because other parts of the, like on the other side we have an inverter that is going, has output going into one of the gates here, and the thing works. So it must be, should be working. But maybe, I mean, it could be that this single gate is broken. So maybe just like, maybe we try the next one, like 11, and I need some jumper wires for that. So if we connect this to this inverter here, and we measure yellow now from here. Oh my gosh, what's happening? This is bad. This is wrong. Why does it not drop all the way down? Okay, wait, something is really weird with that chip here. So oh crap, sorry. Be careful, the schematic is rotated. Yeah, I know. So here's from left to right, and here I'm going from right to left. But look here. So what I just showed here. So here it was connected before, right? Wait, let me disable second channel for a moment. Right, you see the nice square wave going from 0 to 5. Now see what happens. So I wanted to take this output now into the other, in the second inverter here, and suddenly I'm halving this. Do you see that? So I'm connecting basically pin 13 with pin 11 here, basically just putting the same input into, you know, another inverter, and then this happens. Let me completely unplug this one here, and let me go from here there without, maybe this inverter is really broken up there, I don't know. Let's go directly here. Okay, let's measure down here. So what is up with this inverter here? Why is, when I am in, wait, is the pin out? Am I just fucking up the pin out? Can you try to remove the second LED? Like the blue one? So so here on like 40 on the bread, like this green wire here is the output of the clock. If I go directly here to the oscilloscope, we see a nice square wave. All right. So now I want to go to an inverter here. And so I could go into pin 13 or pin 11 or pin 9, correct? So 13 would be the one right next to VCC, so it would be here. That's 13. And I plug in, we measure the clock, it's all good. And now I plug it into, so 12 would be the output of that inverter, and so 11 would be the input of the other inverter. And when I do here the same, now I get this signal. And if I go two further down again, so this should be the inverter number 9, and measure there, we see the regular clock signal again. Let's see, can we measure the inverse of that over here? No, that's just consistently high. That's so weird. Put one channel on the input and the other on the output oscilloscope. Yeah, that's what I did before. That's where I saw like completely weird stuff. So if I put this at the output, the second channel, then I have this consistently like high thing, like that was broken before. Load the output of the inverter maybe. That's what I thought I did with the resistor, but that was stupid, I guess. If I plug in the resistor to ground, Isn't that acting as like a load or not? Am I stupid? I mean, it's very likely I'm just stupid. Let's try another LED here, I guess. So the output could be like this. And then we take another resistor. See, the LED is consistently on. So let me try to show you. So right now, okay, it's shitty to see, but okay, so here you should see the output where I'm plugged in right now. That should be pin 9 and 8 of the inverter, all the way here over here. And 9 would be the input, and the LED is on pin 8, the output. And it's just consistently on. Maybe I should look up this chip. Maybe mine has a different output. That could be another reason for error, I guess. But that would, but they I don't know. That shouldn't happen. And if you reverse the LED, will blink. Why would I reverse the LED? Then it wouldn't light anyway, because that is ground. Are you sure that this is the inverter I see? Oh shit. Thanks for the sub, False Honesty. Yeah, it was the wrong chip. And I thought, wait, but now I have introduced some other bug. God damn it. Why is it not blinking anymore? Can I do Control Z and go back and undo what I just did? Why is it not working anymore? What did I screw up now? Turn off the power before changing things. YOLO. Yeah, maybe did I now fry a chip accidentally? I don't think so. Does anybody remember in what button state I would expect the clock to be, like the regular clock? Okay, so recap. Sorry for the silence. I was so annoyed at myself. So indeed, I connected to the wrong chip. This here is the inverter, and so I thought I just hooked up an inverter there and turned it on, and then suddenly the clock was broken. Now I ripped back out the cables again in the hope that that would fix the clock, but I think I just screwed up something else now. So here, up here we have an and it takes oh, I think I ripped out something that I shouldn't have ripped out. Okay, wait. So I need the schematic again. I ripped something else I shouldn't have ripped out. Oh my god, now it's the stream so much over 3 hours again. Well, oh man, I'm getting annoyed. Sorry. Okay, so up here we have the and that should be the and. Halt! That's what you mean. I understand what you're saying. I know what you mean. Halt. It's blinking again. Oh, god damn it. Thanks, David Panic. And thanks, Toby. Yeah, Halt was missing. I was screaming at the screen. I'm so sorry. My god. Oh my god. Okay, great. So now let me fix this again. Now we take the output Okay, let's turn off the power real quick. We take the output of the clock here, this one here, and take that as another input to this inverter chip here, like that. And then we take the output here, so the output would be right there, but I again use a resistor and put an LED there. Okay, let's see. There it is, the inverted clock. The hold line is flawed, just connected to ground always. Yeah, maybe because we don't have a hold instruction yet, maybe I should add a hold. Okay, so now the inverted clock works. It's always the inverted state. And that's how you build a police car. Okay, one last measurement, just curiosity, even though we probably don't measure much. I want to measure the difference from the output up here and the output down here after it went through all the logic gates. Probably we don't see anything, but I'm still curious if we do. Like, I just want to have it measured just to know that it has no effect. So that would be up here, one measurement, and one measurement here. The stream is hardware gore. Oh, I'm sorry. Why is this half? Did I? Oh, yeah, current. Wait. That's not because of the resistor, is it? Shouldn't be. Oh, wait. Oh, scaling. Sorry. Ignore me. It's the scale. Second channel was set to. Okay. So now let's see. Oh, yeah, okay. There's no really measure. I mean, there's no really a delay. What scope do I have? It's the Rigel DS2072A. It's the one that you can unlock. It has originally 70 megahertz, but you can crack it to, I think, 300 megahertz or something like that. The edge is so ugly. Well, we are also zoomed in like crazy right now. So the time division right now is 50 nanoseconds. So each square here is 50 nanoseconds. Now each square is 10 nanoseconds. I mean, what do you expect? Now if you go like, that edge disappears. Now we have 2 microseconds. No, 5 microseconds. But if you are looking for an oscilloscope, so I bought this because I used it at university and I liked it and I knew you could open it up. However, like about a year after I bought this one, Keysight came out with an entry-level scope that has I think on better specs than this one not cracked. which is I think even cheaper and has more megahertz, also dual channel I think, or maybe even more. You need to check again. But what I remember was that if that would have been out when I thought about buying this one, I might have gone with the Keysight instead. Exclamation the command downtime works too? I didn't know. Okay. Cool. We did it. We finished the clock signal. Oh. There we go. What hertz is it running now, the LED? Right now it's running at 2.7 hertz. But we just measured it with the oscilloscope. I don't know if you were there or missed it or something. This whole thing can go up to 500 hertz. Pretty precisely 500 hertz. Here we can measure it with the oscilloscope. It shows here the hertz. So right now it's running so fast that you don't see it blinking anymore. So 500 hertz is the maximum speed of this computer. Oh, there was another subscriber 8 minutes ago. I missed it. I'm sorry. John Hammerling, thanks for the sub. I need to start building my 8-bit PC. I have all the components ready. Nice. You should. Another energy drink and go for the registers. Yeah, I wish I could do that. So yeah, if there are any questions left, any comments remaining, I think I will wind down the stream in like 5 minutes or so. What speed will it be set? Well, that's the thing. It's settable with this knob here. You can change the speed of the CPU. So I won't set it to anything because we can adjust it however we want. Also, we have the switch here that we can move, and that will give us the ability to do a clock cycle per click. And so later we can then use that to debug the CPU and slowly step through, and we can, use a very slow hertz like this, or even slower, to really watch slowly the CPU executing the instructions. We will have LEDs throughout the CPU to see the different connections and states, and so we can then watch the CPU executing it. Yeah, Benita retweeted or responded or something on the stream. That made me really happy. Are you going to make a pulse modulator, so sending a stroke? I'm not sure what you mean. I mean, that's the clock module. That will provide the clock for the whole CPU. Is that what you mean with the pulse modulator, or is that something more fancy? I don't know. I'm an amateur. Do you have any electronic studies? Not really. I had the basics of, logic gates, or like, combinatorial logic and binary logic and stuff like that in university. I had like what we did, for example, in school. I was on a technical school. We, for example, simplified truth tables like gates, you know, like you do this KV diagram and then you simplify it and stuff like that. That's as much as I did. And as an amateur, I have played around with Arduinos and stuff. That's also why I have a little bit this kind of equipment here. So I don't, that's my background, very amateur. And haven't spent even close to the hours I've spent on software stuff. So yeah, I probably haven't reached 1,000 hours with electronic stuff in my life yet. Make a giant PCB with the computer. Yeah, somebody else mentioned it earlier. I think it would actually be cool, and I'm sure somebody has already done that. Ben Eater's 8-bit computer on a big PCB. I think that would be kind of cool. Maybe we can do this when this is all done. Make it into a big PCB. That would be kind of cool, but I mean, that's something for the future. I mean, with that modulator thing that you send 3 times a clock fast and then wait a bit, then 3 times fast to see the next instruction directly. Oh, I think I know what you mean now. Because, like, let's say each instruction takes 3 cycles. You mean that you can send all 3 quickly as as a kind of like a single step, and a single step is 3 clock cycles, for example. I guess that's what you mean. I don't know if is Ben Eater building that. If he is building that, then I will also probably build it. On the other hand, might also be a fun debug thing, maybe, to have like a... That would be quite a challenge. I don't know. Like that sounds simple enough that it should be doable, but definitely hard enough for me. I would not know how I can make a single click and have it followed up with 3 clock cycles. I don't know how you built that with a circuit. Is that easy? Yeah, I don't know how something like that works. Would you need to have a small counter, like you always set like 2 flip-flops to the value 3 and have it like decrement or something like this? I don't know how you would do that. That would be maybe interesting to learn. With counters, I guess. Yeah. More 5x5s. Yeah, I was also just thinking, could you maybe time it with 5x5s? I don't know. Like you have a 1 5x5 generate just a regular unstable pulse, right? But have another one that is ending that one. So you have it on for always 3 times as long as the first one. That could also maybe work. That sound reasonable what I said? Basically we combine this one here that just stays on longer and will always stay on 3 times as long as this one here, and then you end the 2 together, and then you should have 1 click should always output 3. What's the next step for the computer? Yeah, I'm not actually sure how we continue, because I've seen the next videos he did was on the SR, Latch, the D Latch, and the D flip-flop. So, and all these videos together are quite long. So that's like 40 minutes or so to watch those. But I guess that he did that in the series because it's kind of important at that point. So we definitely want to watch that. Okay, so maybe, and then maybe the next video is also just next minute. So maybe next stream will be less building and more just watching and maybe theorizing a bit about it. Maybe we can, I mean, he's also basing this on on something that he's building there. Maybe we have the parts and we can replicate it. So that will be the next stream, I guess. Oh, I didn't show my screen. I'm sorry. So the next episodes in his series are just about the SR latch, the D latch, and the D flip-flop. And so these are more like theoretical. So yeah, that's what we will continue with. Is this gonna be on YouTube? It will be unlikely be a live overflow video, just because why would I make these videos that Ben Eater has already made? Makes no sense. I think it's fun to have like a live stream instead about it. I see a bit more value in that, I guess. Maybe I will do like a summary video when it's done, maybe, for live overflow. However, all the videos will be in the Twitch archive, and also I will upload them on a second channel called Random Overflow. You can find the link to Random Overflow channel on the Live Overflow channel when you look in the sidebar in the featured channels. This is where you can find just the recording of these streams. Yeah, that's why it makes no sense for me to make videos. Just watch Ben Eater's videos. They are great. They are perfect. Maybe make everyday highlights video. Well, that's also kind of a goal that I have. Once I stop the stream, I will make a rough condensed cut of this stream. So to condense these almost 4 hours into like 30 to 40 minutes, just a very rough cut, which is I think already better than watching 4 hours. So that's the plan. I'm not sure if I can keep that up with my other responsibilities. You are the 21st sub of Random Overflow. Wow, I got a few subs since the last I checked. From 0 to 10, how much do you think you understand computers and electronics from the electron and up? I don't know how to answer this question. I don't know. Like a 3, maybe? Oh, Cynthia Ref, are you on Twitter, Cynthia? But yeah, the bot will be available. Bye, Quizlex. Okay, let me finish the live stream. We succeeded today. Bitsend on Twitter. Yeah, cool. Nice for coming around, coming over. Nice for visiting. Here's a micro instruction video with the concept. Thanks for sharing. Okay, all right. Thanks everybody for joining me today. Thanks so much for the bits and the subscriptions, and most likely see you tomorrow, continuing building this. Have a nice evening. Keep on learning, and see you soon. Bye bye.